Okay, this is sample problem 17.4. Calculate the pH of the titration of 50.0 milliliters of 0.120 molar acetic acid, that's a weak acid, by 0.240 molar sodium hydroxide after the addition of 10 milliliters of the base, 25 milliliters of the base, and 35 milliliters of the base. Okay? So what I'm going to do, this is a titration problem, is I'm going to find the number of millimoles of everything. So let's find the millimoles of the acetic acid. Okay, the volume is 50 milliliters, the molarity is 0.120. So I'm going to take 0.120 moles per liter and multiply that by 50 milliliters. Okay, so that looks like it's somewhere around 6. Let's try it. 0.12 times 50. Yeah, 6 millimoles. Okay, so we have the number of millimoles of acetic acid. And then in part A, the number of millimoles of sodium hydroxide would be, let's see, we got 0.240 molar, and it's 10 milliliters. .40 millimoles. Part B, it looks like we have 25 milliliters. Okay, so millimoles of sodium hydroxide. Again, it's 0.240 moles per liter times 25 milliliters. So that's 2.5 as much. So that would be what? 4.86, right? 6 millimoles. And then part C is 0.240. And now it's 35 ml. All right, so that's 0.240 times 35. 8.4. Okay, so it looks like what happens is in part A, the excess reactant is the acetic acid. In part B, it's the equivalence point because they're equal to each other. And then in part C, we have excess sodium hydroxide. Okay, so let's do part A first. In part A, we have acetic acid reacting with sodium hydroxide, forming water and sodium acetate. Okay, the number of millimoles of the acetic acid is 6. For the sodium hydroxides, it's 2.40. This starts off as 0. We subtract the smaller amount of each reactant. So plus 2.40, and we get 2.40. Okay? Now the significance of this particular part of the problem is that we have excess weak acid, and now we have in the same mixture its conjugate base, which means we have a buffer. When you have a weak acid with its conjugate base, you got a buffer. So there's a buffer solution. So that means the pH is equal to the pKa plus the log of the ratio of the concentration of the conjugate base divided by the concentration of the weak acid. Okay, now we could go ahead and calculate the concentrations by taking the number of millimoles of each, 3.60 and 2.40, and dividing that by the total volume. But the volumes would divide out because they would be in both the numerator and the denominator. So it's easy enough just to go ahead and put in the number of millimoles. pKa is minus log of the Ka. This is acetic acid, so it's minus log of 1.8 times 10 to the minus 5 plus the log of 2.40 millimoles over 3.60 millimoles, right? Conjugate base over weak acid. Millimoles are going to cancel. So it's really the log of 2/3. 24 over 36 is 2/3. 2.40 over 3.60 is 2/3. The negative log of the Ka is 4.74 if you put that into your calculator. And so this would be the log of 0.667, right? 2/3. So all we got to do is add that to the 4.74. So 0.667 log plus 4.74, and you get 4.56. Okay, there we go. Part A is done, 4.56. So I'm going to go ahead and write over here, pH equals 4.56. Okay, so that's one type of problem where you have excess acid, right? In part B, we're not going to have excess acid anymore. Oops. Lost everything there. Okay, part A. Let's just do it this way. There we go. Let's surround this and just get this part through here. There we go. Okay. In part B, the number of millimoles of the sodium hydroxide is no longer 2.40, it's 6.00. So that means that we have stoichiometric amounts of reactants. So they're going to be 0. So once this reaction is complete, we have 6 millimoles of the sodium acetate. Okay? So that means we have a weak base problem. We have to figure out what the pH of 6 millimoles of sodium acetate in a volume of, it looks like 75 milliliters. What's the pH of that solution going to be? Okay, so CH3COO minus, I'm going to take the sodium off just so that we can show it as a conjugate base reaction. The sodium is a spectator ion. Water will donate an H plus to the acetate to give you acetic acid and hydroxide. That's why it's a base. It forms hydroxide out of this Bronsted-Lowry reaction. But to figure out the pH of a weak base, we need two things. We need to know the initial concentration of the base, and we need to know the Kb. So let's find the Kb first. Kb is Kw over Ka, where Ka is the equilibrium constant, the acid dissociation constant, for the conjugate acid of the weak base. Well, the conjugate acid is right here. It's acetic acid, and it has a Ka of 1.8 times 10 to the minus 5. So this is 1.0 times 10 to the minus 14 over 1.8 times 10 to the minus 5. So when you do that, you get 5.6 times 10 to the negative 10. So we've got our Kb value, but we also need to know the initial concentration of the acetate. Well, that's going to be the number of millimoles of the acetate, which we already know, 6, right? It's the product of the previous reaction, divided by the total volume. The acid had 50 milliliters, then we added 25 milliliters of base, so it's 75 ml. So 6 millimoles over 75 milliliters. 0.08 molar. So there's our initial concentration of the base. See how I'm going about this? Plus x, why? Because Q is equal to 0, so Q is less than K, so the reaction goes to the product side. Okay, so now that we've got that situation set up, we can go ahead and start doing the calculations. Again, this is really a lot of calculations in these problems. It's pretty intense. So you have to really you have to be very organized when you do these problems. Okay? So KB is 5.6 times 10 to the negative 10, and that's equal to x squared over, I'm just going to go ahead and cut 0.08, right? Because that minus x is so small compared to the concentration 0.08 that it's negligible. So that means that x squared is 0.08 times 5.6 times 10 to the minus 10. So that means x is the square root of that. Okay, so 0.08 times 5.6 times 10 to the minus 10. Take the square root of that, and you get 6.69 times 10 to the minus 6. Okay. Well, X is the hydroxide concentration, so that means POH is the negative log of that. .17. So pH is 14 minus that. Looks like it's around 8.83. Okay, so we got two of them. We just have one more to do. So let's go ahead and clear all of this out here. Okay, so now the sodium hydroxide is no longer 6 millimoles. Because we now have 35 milliliters, and that's 35 times 0.24. So I'm going to come back over here again. 35 times 0.24, 8.4 millimoles. That was a piece of information we had before, but got lost. Okay, so now the excess reactant is sodium hydroxide, and the limiting reactant is acetic acid. So we subtract the smaller of the two. Of course, this is 0, and now this is 2.40. Now, this does go up by 6 on the product side. But what happens is, again, that's a weak base, and weak bases do not affect acidity nearly as much as strong bases do. So we can ignore the weak base if we have a strong base. Unless the strong base is such a small concentration that the weak base is a higher concentration, significantly higher. Now, it's true the weak base here is a higher concentration. There's 6 millimoles of that and only 2.4 of the strong base. But that's not a big enough difference to make much of an effect on the pH. So we're just going to deal with the strong base. So we have 2.40 millimoles of the strong base. And our volume is 50 plus 35. That's 85 milliliters. So 2.40 over 85. 0.0282. That's how much sodium hydroxide is left after the reaction. So the POH would be the negative log of that. $1.55. And the pH would be 14 minus that. $12.45. Okay, there's our three values. We've got them all there. Acidic, basic, and then very, very basic for part C.